Have you been well?
Pretty good. Yep.
Okay,
How are you?
Very good.
that's wonderful. Who can remind us what we learned and discussed last time when we met?
Memory allocate.
hmm Memory allocation. And what things did we learn about when we learned about memory allocation? Yep. Today I'm trying out this YouTube live on when I Zoom, like when I teach. So I'm going to see how well it works. So that's just to let you know that I'm doing that. Yeah. Somebody says, Louis says, if by any chance I keep leaving joining, it's because I'm having some slight connection issue due to power leaving in my area. I'm sorry about that. We had a lot of snow this side. I spent some considerable amount of time this morning just plowing the snow and had a plower guy come, and it was just too much. Still, a lot of decks have to still be cleared of snow. So I had to start completely, Louis. All right, guys. So what did we discuss last time? Again, you can put on the chart there. Oh man, Kevin, sorry, I can barely feel my fingers because of the snow. Sorry about that. Sorry about that. Yeah, I've been showering like, mad through. So Diane says malloc, realloc, and calloc. Yeah, that's correct. That's what we discussed about last time. And I'm going to quickly revisit that. So I'm going to share my screen with my screen with you. It's coming up. You can see it, I suppose. Can you see it?
Yes.
Okay, that's wonderful. So let's do it. So we learned about dynamic memory allocation. So I'm going to put something like this here, just as like a comment, right? So and say today dynamic memory allocation. So and I'll save this in a .c file. Okay, and I will say I'll say allocation .c so that we can remember it. And during the course of the learning, I am going to share this file with you. I'm going to share this file with you. Thank you so much for all the folks who have turned on their videos. That's fine. Thank you so much, Colin, Ethan, Benjamin, and Hirech. For the others, thank you for putting on your picture onto your account. Others, Aiden, Peter, Jon, please put on your pictures if you cannot be able to switch on the camera. It's nice so that I don't see just blobs of people in my screen, right? Okay, so we tackled last time dynamic memory allocation. Who can remind me what sort of file do we need to include in order to work with these kind of things? What include do we need? What preprocessor directive? We need an include what? Someone?
Standard lib.
Sorry?
stdlib.
stdlib, yeah, that's true. So we need stdlib to be included. We need stdlib to be included because it's an stdlib that we can be able to do dynamic memory allocation, malloc, calloc, realloc. Those files are defined in there and created in there. So that's important. Okay, we can also include stdio, standard input output, because we want to print out stuff, standard input output .h like that. Okay, so we could do that include stdlib because I can say here for using dynamic allocation, etc. And we know that stdlib here is because we are going to use printf, scanf, etc., etc. And so we can declare our main like this, void. And when we do that, we can then do a couple of things. So remember, we are just revisiting this concept of creating arrays dynamically. So the context is, if we do not know how big we need our array to be, and therefore we cannot really ask the memory manager to get that memory for us on the stack frame, then the best thing to do is to create some variable, for example, int n, which basically would be number of items stored in the array, something like this. Okay, and we can read this. So okay, so we can say printf, and then I can say %d like this, and we want to put this in the address of n. Sorry, no, sorry, enter number of items, or maybe just quickly say enter size. Okay, so this will enter your size. Sorry, I need to have this thing over here. And then we'd use scanf like that. And now we put this to the address of n. So we can read an item now, and we can make as big as an array as this number of items here. So what we said is we want to get this memory from the heap. So we can say int maybe names. Remember, we have to declare the pointer, and the work of this pointer is to store the address of the first byte of this block. Let me repeat that. This pointer that we have, this pointer, let me write it here. This pointer shall store the address of the first byte of the array. So, well, the address of the first byte of the array means also the address of the first item, so to say, right? The address of the first item, because to be the first byte where the block starts. So if we, let me get a pen here. So if you are looking at the array as something like this, and this the first index, second index, index 0, index 1, index 2, index 3. What we want is this pointer nums here to store this address here. Now, this also will be the address of the first item. It will be the address of the first item of the array. So that's what this is for. And if we go back, remember, we are going to have the heap here. This is going to be our stack frame. And of course, we said that this section here is storing our instructions. And this one is storing our global variables if we have any. Okay, if we have any global variables, they're going to be stored here. So these pointer, remember what we said, pointers are variables that we use to store addresses. So these names, it's memory. This variable, it's in the stack. We have something called names, but it's in the stack. Does that make sense? We have something called names, this pointer, because pointers are variables, right? Pointers are variables whose work is to keep addresses. So this must be defined because we are not able to communicate with the things in the heap unless the addresses in the heap, unless we have a way of storing those addresses. All right. So now when we do something like this, let me get the pen again. Now we can say names is equals to, right? We assign, first of all, we call malloc. We want n items, and each of these n item is going to be size of whatever number of bytes we use to keep integers. So remember, malloc returns to us, okay, the address for a certain block. Now this block here is this. So n times size of whatever. So if n is 10 and an integer is being kept in 4 bytes, this will give us 40 bytes. Okay, so we are getting, malloc is going to return us the address from the beginning of those blocks. But because it's going to return this as a void pointer, we want to typecast this again to become an integer pointer. So that's what we are doing up there. Now, so that's quite cool. Malloc can return. So I'll say here, malloc returns void pointer, like that. So malloc returns void pointer like this, and therefore we want to typecast it to the integer pointer because we need to keep an array of integers. Now, if malloc does not get any addresses, or there's no memory for us to be assigned, what else can it return? What will it return if there's no addresses? Someone? What will malloc return if there's no address?
Is it null?
Null, yes, of course.
Null.
It's going to be null. So if there's no memory, we can say if nums is the same as null, which basically means no memory is there. We could even tell the person using it and say printf, well, no memory. No memory, like that. And then we can either exit this code if you're not going to, if, well, the code was just for us to just create an array and then process this particular array, then we can exit this code if we cannot be able to keep that. So that's basically number one, what we could do. Remember, instead of using malloc, we could still use calloc like this, but then instead of giving only one argument to it, we can just put two arguments like this. That means give us n items each of this number of bytes. So we could use callocate, or we could use malloc, still would work fine. Make sense? The only difference, we say that callocate will initialize all the items with zeros if we are keeping integers. Can also do that, if we are keeping characters, there'll be all null characters. If you're keeping pointers, this will give for us just null in every location for it. Okay, so we could use calloc, we could use malloc. It doesn't matter. I'm just going to use malloc.
Can you say like the difference between malloc and calloc again?
Yeah. Okay. So actually, we talked about that last time. So why don't I do? Let me see. So calloc takes in two arguments, right? One of them is the number of items we need and how many bytes which are required for each one of them. Okay. Now let me put it like this. So I'm going to do copy that, paste that. I'm going to do malloc here, and I'm going to do that. So notice the difference. Here we only need one. This only one argument here, n times size of that. So basically we can replace this number with saying we want 40 bytes, for example. We could replace that and say we want 40 bytes. But well, because we don't know how many bytes are being stored for an integer, we can just say give me n times size of whatever number of bytes integers are being kept. So this is only one argument, and calloc is two arguments. One argument here for the number of items you need and how many bytes you need to keep one of them. That's one difference between malloc and calloc. Another difference is calloc will reinitialize, everything in the array with values. So if we are keeping integers, all values are going to be zeros. If we are keeping characters, all things are going to be null characters. If you're keeping pointers, everything's going to be null. If you're keeping floats or doubles, everything's going to be 0.00. Okay, so callocate initializes these with 0 values, whereas malloc does not initialize them, which means the values which are going to be in the array are going to be garbage values. Does it make sense? Okay, so that's main difference between them. But in any way, both of them, malloc and calloc, will return void pointers, and we need to typecast that to the known type or to the data type that we want. So far, so good. So we must always do these to try to catch the error returned by the failure for malloc to allocate memory. Okay, so that's what here we are doing. All right, so I'm going to remove one of these. Let me remove this guy. And so this should be all fine. So we have this. Now the next thing we did, we could put some values to this. So we run a for loop. We get an iterator, int I equal to 0, I less than this number of items, and I plus plus, and then we start printing. We put things into the array. So remember, there are a couple of things we could do. If we wanted to assign things to an array, we could do nums, and then we could do for the ith index, put some value. For example, we are using a rad operator, and let's say use rad, for values between 0 and 100, for example. Okay, so that would give us that, and we could print our array, right? So this would assign us values. But because one of the things that we know is this, that the name of the array, for example, the name here is nams. Nams basically is a pointer that is storing the address of the first element of the array. So we could just do nams. Sorry, well, if we did nams at 0, which basically says, give me the value at the 0th, is just the same as saying dereference nums. These two things are equivalent, correct? So we can put some sort of equivalence here. These two things are equivalent. In order for us to go to the other memory blocks, though, we could say nums I plus whatever I value is. We put that into parentheses like that, and then we dereference it. So these, whatever, if I remove this guy here, the 0, and I put I here, this and this are equivalent. Turns out actually that also this is equivalent to them. We could also do something like this, and it should still be equivalent. Now, this is not the standard. Remember, we said we are going to be using standards, in C. ANC standard. So we're not going to use these, but it works. It's legal to use it. It's fine. These are the two most important things that we can use. But because we are learning about pointers and dynamic memory allocation, we'll use these. Important though is to actually understand that these and these are equivalent, and that these now they are static in this case, and the square brackets all mean dereferencing operators. Dereferencing. So both of them are dereferencing operators. If you look at the difference between this guy and these guys, we just have square brackets here, and here we have they're static, right? Both of them are just giving us the value. So the square brackets and the static, they are both dereference operators. We are just dereferencing with them. So in this case, instead of putting that, I can just say nams plus I like this. That will give me the address, and then we dereference that to get the value. Remember, the assignment operator is a right-left association. So this will be computed first, and whatever value we get it, then get assigned to here. Okay? So remember, the assignment operator has a right-to-left association, which basically means the rand function will be called, will get us an integer between 0 and 99, or between 0 and 100. It gets us that value, and then we put that value in here. And we can print this if we wanted. Let's print it. Print F. Remember, again, as I mentioned, so this, we are printing integers here. We're printing integers, maybe a new line after printing the integer. And which integer are we printing out? Again, I can just do the same. I dereference the address pinpointed by these things over here. So far, so good? Now, so okay, this will print out everything, so it's fine. Remember, we used malloc to allocate memory. So once we are done, we need to free that memory. So remember, when we do dynamic memory allocation, and like in the stack frame where there's some sort of memory collection, memory collection by the memory manager. In this case, it's upon us to do to allocate memory and to free the memory. So we'll say free names, okay, and then we say return 0 over here. All right, so let's save this and try to see it in operation. So I'm going to get the shell over here, okay, and I'm going to clear this. So we're going to move to CD to my desktop, and I think this file is in the comp 1020, and this is SP 1020 like this. No. Was it a file like that? Was it 1020? No, SP 2021. 2021 like that. 2021. Yeah, that's a file. All right, we do that, and then we are working on allocation.c. That's a file we are working on. Okay, so let's go on. We compile it. We are going to call our output the name file. This is also good to call it whatever we want. Allocation.c, runs it, no problem. Everything compiles properly. We try to run this now. File, enter site, the number of items we need. Maybe we want 5. Okay, now we can get all the 5 values that has been given to us. I can do this 2D here so that we can have the width to contain 2 items so that they are all in a line. It's always good to to have something looking nice. So because I have done now, if I run it proper, file, enter items 5, you see all of them, they are in some sort of nice line, 2 items. So they're all in line. That's good. So this is how we'll print out items. Again, we are sending items using the idea of pointers, and we are able to print them out like this. Now, if we wanted to print out address for each specific items, remember in the past, we could do this. We could say address of nums, at the ith index. This is how we would print out the address of each single items in the array, right? This is how we could do that. Well, turns out instead of, because we already know what these square brackets would mean, we could remove this guy here and just add I plus I. And that is equivalent to getting address. And how do we know that? Because names here means the address of the first element of the array. So when we add I here, we're doing pointer arithmetic. So let me get it like this. So imagine that the address of the first element is, say, B10, and we are keeping integers. So nums plus I means B10, the address, plus I, but now this is I multiplied by the number of bytes needed to store one individual, to store one element. Okay, so in this case, if the elements that we are trying to store here are, if the elements we are trying to store here are integers, so this will be 4 multiplied by whatever I is. It's almost like we are shifting. So if I is 0, then we're just going to return B10. If I is 1, it will be B10 plus 1, so it will be B14. So this is how, if the array looked like this, and this was the address of the first element, so this will be B14 here, this will be B18 up here, this will be B22, and how we actually go to every single one of them using pointer arithmetic is just to add an I here, which basically then qualifies to this idea. Okay, let's see that in operation again. So we clear this, we run it again. Okay, file does it 5 items. Okay, I think we have not started printing it out, so we're just going to say percentage P here for pointer, and but this is going to print out the addresses in hexadecimal numbers. So let's run it, no problem. File comes out 5 items, and you can see the addresses up here. So 80, 84, 88. This will be then sort of 92 because of hexadecimals. We get C instead, right? Okay, we get C, like instead of like 12, we get C. Okay, and then we're able to go back and forth with it. You can see that? Is that all good? So every single one of these items then, let's actually print something here, which is going to be the address, printf, the first element. Again, remember this is sort of revision, right? By now, you should be able to know this, %p, which is here, address of first element. Which is, we can know the address of first element of by just typing up the name of the array, which is names in this case. So if we do that, we run it, no problem. File, 5 items, and you can see the first element is at this address here. The first element is this address here, 4080. And if we look at the first element that we are printing out at index 0 is 4080. So, and that can conclude that the name of the array is a pointer that holds or keeps or stores the address of the first element. And every single item from there, when we do plus I, when we do nums plus I, when we say this number 4080 here plus I, what really is happening is when I is 0, we get the same thing. But when I is 1, because we are multiplying with the number of bytes used to store one single element, which is 4, when I is 1, then it will be 4080 plus 4, which become 84. When it's 2, it will be 2 times 4, which is 8. So 4080 plus 8, which is 488, and vice versa. Okay, so the idea here is that if we know the address of the first element, by knowing the name of the array, we can be able to know all the items with the array by just doing pointer arithmetic. So far, so good? Awesome. So that's example 1. Like this, student ID, and this is going to be a float, student GPA, something like that. So now we have 2 items. Oh, sorry, did I freeze?
Yeah, you cut out for like a few seconds.
Okay, I didn't notice that. Maybe the internet box. Maybe I need to put, yeah. Okay, so I don't know what happened there. We do type def. Remember, we are sort of creating a synonym for this. We are trying to create a synonym for this guy here, struct student. So we'll do type def, struct student, and we call it a name like student, something like this. It's always good to come up with meaningful, names, right? Meaningful names. This is important so that we can know what you're working on. So we have now created something called struct student and renamed it or created a synonym for it called student. So this will refer to the same thing. Okay, I'm going to clear this and I'm going to move forward. Now, well, in the past, we have just made, normal variables of type students. Remember, we could make arrays of type students. So in here, instead of having now something called names, which is a pointer to integers, or is a variable that keeps addresses of an integer, I want it to keep addresses of a student. So instead of int, remember, student is our own data type. How many bytes, by the way, do we require to keep just one instance of student? How many bytes do we need to keep an instance of students? Yeah, how many bytes do we need to keep an instance of students? Yeah, Jaila, I think I like that. Bytes of integer plus bytes of float. So if an integer is kept in 4 bytes and a float is kept in 4 bytes, which is normally the case, then one instance of students requires 8 bytes, right? Requires 8 bytes. Vian is not 12, is 8 because float is 4, double is 8. I think that's where the confusion is coming from. All right, so we'll possibly require 4 bytes. Now, we want to create an array of type students. Remember, there's no major difference to our normal arrays. So instead of having an array of integers, we're going to have just students. Let's rename this array maybe to make it more nice and call it my student. So my student is a variable, okay, that keeps addresses of item of type students, which is the same as what we had before. Nams was a variable that was keeping items of type integer. But now here, my student is a variable that keeps items of type students. You know, it keeps addresses of type students. We can do the same thing. I just put my student here where nams was. And instead of integer here, I want to typecast it to type student. So that's my own type. I put student in here. It will say malloc. And instead of integer here, I'll just put student. See how that happened? So instead of using the primitive type integer that we had before, we created our own data type that we have learned how to create, and we can use it to create our own arrays. The only major difference actually is that for each, if we were to draw the array like this, every block here is made up of 8 bytes, 8 bytes, 8 bytes, 8 bytes, or as big as the number of things of member variables that we have in an array, right? In the struct. Does it make sense? Can you hear me? Okay, good. Can someone speak actually?
Yeah, we can hear you. I have a question actually. Two
Go for it.
questions. So, because that like holds, or at least like the size is like 8 bytes, so there'll be 2 different values in each of those indexes?
Yeah, so in here, oh, that's a good question, Jaira. It's an excellent one. Struct student will have 2 things here. One of them will be student ID, and one of them will be student GPA, to read something like that. Does it make sense?
Yeah.
Yeah, and if we had more items, yeah, we'll just have a big one with those kind of things, and we can explore that. I think that's going to be key to actually explore. All right, so far so good, yeah. Now, because we are using pointers of type struct, you know, pointers to struct. Now, so this would work fine here, my student. So I'll replace nams here. And I say if my student is null, no memory exit. So all this again should be fine. Something we should be able to know. Address of first element, I can just replace that with my student. Again, that should give us the address of the first block, And then in here, we can just put the items. For int I equal to 0, I less than n, I plus plus. So we want to type, to do all the items. There are 2 items to be kept. So remember these here, let me get it. Remember here, my student plus I, if we typecast this, is equivalent to this, is equivalent to my student, I, like that, right? Remember, this guy here we had before is equivalent to this, correct? Yeah, it's completely equivalent to this. The only thing is that we are trading the square brackets to these asterisks that we have up here. So they are the same. They are completely equivalent. So if we were to take that as dereferencing the address, because we are dereferencing the address there, like this, we can take it like that, the whole block, to mean this is this. And then we can look for each member. So we can say dot student ID, and then we can get some value here. Then I can copy this. I paste it again, and I just change here student GPA. Does it make sense? So I'm going to each and every specific items within the array. Now, well, if I'm trying to print them out, it should be the same. So I should just copy this guy, and I can just replace here. And I can do that for this guy as well, copy. And I can print them here. Okay, and then I can do that. And instead of nums here, I'll have my student plus I. My student plus I. This will be the addresses, right, for each block. Okay, this was GPA and ID. The GPA, so we get here percentage dot 2F, right? So because it's a float. I hope this works. Something like this. Okay, and percentage P will print for us the address. Okay, then we free my student. So I'll just going to copy this, and I'm going to paste it here. We're going to save this, and we're going to run it. Okay, no problem. Is there any person who does not, who basically is either confused or would want me to sort of revisit what is happening up here? Do we understand it? I know sometimes it can be confusing, and it's fine if you, if somebody gets confused about it. Important is to think about this, that this bit here, this bit here, this bit here is the same. This bit here is the same as saying my student at index I. But remember, each index, if we had my student looking like this, like a big array, and we have block 1, block 2, block 3, and block 4, each block, index 0, index 1, index 2, index 3, each of them is also divided into the ID and to the GPA. See, every one of them looks like this. It has an ID and a GPA. So what we are doing is we're saying, go to my student index I. So for example, index 0. And then when we say dot here, the member operator dot, saying dot, get me the ID. Dot, get me the GPA. That's what we are doing. But because we know that my student I, this is equivalent to doing this with pointers, basically taking my student, basically the name of the array, plus I, the index, and then dereferencing that, then we can do the same thing that we have done. Okay. The other thing maybe that could be of good concern and maybe worth asking is, why did I put these parentheses here and also these parentheses here? Now, we are putting these to guard this asterisk here. This is to say, the dereferencing operator, this guy here, we want it to bind to the closest thing that it comes to. If we want to remove these guys here, let me show you. Supposing I removed that, maybe, okay. If I remove these and these, this will assume that it's going to get this address and this whole item together and then try to dereference it. That's what it will assume. But what I want it to do, I want it to know that I just want to dereference that and then go to each individual member. That's why I'm putting all these parentheses together. Okay, then I can use the dot operator because now this will give me the actual place and then dot get me this. And I can do the same for every single everything else. So I'm dereferencing and then using the dot or the member operator to be able to get the items. Now I'll save this. We run it. I think we had run it, but we can run it again. I'll clear this a little bit. Then we'll do file, and it says items 5. We put it together here, and we can see we have 7. I think we maybe the GPA we need to do something else. Maybe we should get it 4 here, and we should make it maybe we make it a float, right? So just out of so again here, we are taking a number between 0, possibly we should do 5 so that we get numbers between 0 and 4, and then we typecast it to a float, right? This is what we want to do. Remember, we want to do the GPAs of students between 0 and 4. So we want RAD to give us a number between whatever RAD max is, we modulo 5 so that we get 0 to 4, and then we make it a float. Okay, so run it, no problem. Run file, 5 items, and now this is what we have. We have the first item with 7, 4.0, and its address. Now, I want you to notice something about the addresses. Actually, why don't we do with %u? I know it's going to complain about us printing out %u because we need to use %p, but it's going to give us an actual value that we can actually compare. So when you see the warning, don't be dismayed by it. Just know that that's what's going to happen, as you can possibly see. 5 items, we get this. Now let's see what happens in terms of addresses. Again, we get all the items that we have here. And if you look at the addresses, I want to just look at the last items. From 68 to 76, I think these are 8 bytes. You see that? Can you see that? Is it too small? Or should I enlarge it? Or can you see it? Should I enlarge it? I can't hear nobody. So I'll assume that's fine. Between 76 and 84, again 8. Again 84 to 92, 8. 92 to 00, 8 bytes. Which is basically equivalent to what I was saying before, that we have a block here. Each block is 8, 8, etc. So that's basically what's happening with these things. Similar completely with how we made the integers look like, only that the integers were just 4 bytes. Let's try to analyze this further and see what else we can do. Supposing I wanted to print out actually, so this would give me the address, but I also want to print out the address for specific items, the address of specific, like the address of this guy and the address of this guy. Remember, I could just do this. I could actually copy the whole thing. I can copy the whole thing like this, and I'm going to just paste it here, but I'm going to put some parentheses like this, and this, sorry, and this, and get the address, right? So that will give me the address of the item that I'm looking for. So that was for GPA. And this will give me for ID. So this will give me the 2 items, the address of the 2 items that I need. Okay, so instead of %u here, I'm going to put another %u here. And let's see how it actually works. So I'll save this. I'll run it. Okay, 2 warnings because I'm using %u. I do file, and then 5 maybe, and then here we are. So I want you to observe a couple of things. Let me make it a little bit. I should make it a little bit bigger. View shell. I thought there's a way to zoom it without having to. Why do you want to do that? Okay. Okay, it's not doing whatever we want it to do. We wanted to zoom the numbers. Okay, so it doesn't matter as long as everybody can see. Important though is this, that then this here, the number, okay, I mean, we should possibly put it as also as percentage U so that we can be able to compare. I'll save this. I'll run it again. No problem. 5. And so the most important thing I want us to look is these numbers over here. Okay, now this is the address of the first element. So if you are going to draw these 5 blocks, block 1, block 2, block 3 and 4, and block 5 here, we have 5, index 0, index 1, index 2, index 3, and index 4, because we said 5 items. The address of the first element is this one ending with 6128, which is here, right? Now, I want you to look at the first thing, okay? So these two things here represent one item. Sorry, these two here. The 7 and the GPA 4.0. So the 7 is the student ID, 4.0 is the GPA. So these two items, but the first item 7 is address is 6128, which is the same as the first one, 6128, 6128, which basically means here we have our student ID and here we have our GPA. And really our GPA, the first item in the instance has the same address as the first block, which is pretty obvious because that's where the block starts. That's where we should keep the first item as well. So this one is 6128, which is basically the first block here. The next one will start at 6132 because you need 4 bytes for integer. So this 6132 here. And then the next one will basically be 6136. Remember, 6136 will go to the next block here, which is 144. But in between here, we have the 6136 and 6132. And then we can go on forth and forth and so on. Does it make sense? So each one of these contains its own addresses, but all these addresses are actually all in one stream. They're just basically being kept in one big block, in one big block, but demarcated for each instance of the struct that we have created. Any questions? Any questions? No? Y'all good? Awesome. So this basically teaches us about dynamic memory allocation. The other thing maybe I should ascertain is this. So here we said that we could do this. Another way we could do this, so remember we are doing two things here. We are dereferencing and using the dot operator. See, dereferencing and this member operator. One of the other things we can do, we can use pointer to struct operator. So instead of doing this, we can replace it with an arrow like that. And then now we can remove these guys and these guys. So that's also the same. So this is the address of the item. And then we dereference that by using the pointer to struct operator this way. So we're using the name. We basically get the address, the address of the of a particular block, and then we use that to get to the member, and that should work fine. We could use that idea instead of using the dot operator as well. No problem. Runs fine. 5 items works fine as well. Okay, so instead of using, basically we're saying instead of using this idea, this is another idea that we can use. Okay, pointer to struct operator. So we can use this guy instead. And therefore, for the rest of the our learning, we are going to be using pointer to struct operator instead of dereferencing and using a member operator to get this. Okay, so let me do this again. I'll copy that guy. I'll paste it here. I'll paste it here. And then here, we are going to use GPA instead, like that. So this is equivalent to this stuff that we have been doing here. You know, it's equivalent to these guys here. So we can just change them, paste that, student ID, same idea, copy this, change for this. Yeah, copy for this. Yeah, should be fine. We could even do the same here. We could change the entire thing and then get the address and print it out. So we could still do that. So this is exactly the same as we were doing before. And I kind of copy this. So remember to revisit this work if you get confused with these ideas or these techniques. Please revisit it, and it will be helpful for you to see what we have just done. So we can just change everything to use the pointers to struct operator to do the same thing that we have been doing. So we save this. Okay, we try running it. Okay, no problem. And 5 items, and it works same as what we were doing before. Okay, now let's change this to P and to P and to P so that we can be able to use it. Okay, so far so good for everybody? Yeah, we are all good? Okay, so we know how to do this. This is awesome. All right, and so I could save this. Let me save this. So we are good with this. Let's explore other things that we could try to do. So we know how to do all these things, and it's quite nice. This code here, we could try to possibly put it elsewhere, right? Let's imagine that we could put this code elsewhere and work with it still. Now, the concept that we're going to learn now is called opaque object design. So we learned today about dynamic allocation, all these. So the other thing I can point out is opaque object design. So what does that constitute? So if we are working with this and we give somebody this code, is that they're going to be able to see that we have a struct called student, and this struct called student has 2 member variables, student ID and student GPA, right? They can be able to see that because it's the code. But imagine we didn't want them to see that. What we could do, which is wonderful, we could just copy these guys here, okay? And I'm going to copy all of them, including these, like that, and I'm going to cut them, okay? And what I'm going to do, I'm going to create a new file, and I'm going to paste these guys here, and then I'm going to save these, save as, okay? And I'm going to call it, say, struct or student. Let me call it student, actually, student. But instead of calling .c, because it is not really code there, it's basically header file. Yeah, it just basically contains some stdlib, stdio, and a definition for struct. The material that I am putting on top of main, right? That's only what this file contains. So I'm going to call it a header file. So I'm going to say .h. So this I'm going to call it student.h file. And I'm going to save that. So now I have a new file as part of my code called student.h. And if you look at it here, so if you like come closer, you'll see allocation.c is a .c file. There's something here written .c file. And this one now is called .h file. You know, it has a h next to it, right? You know, like there's a h next to it and there's a c next to this one. So these are like sort of a .c file. And this is a .h file. So like a header file that I can use and include in my things. So now I have all these materials, stdlib, stdio, and I have the struct that I've created, and I'm saving this elsewhere from my main file, which is this one. And because I want them to work fine, now I'm going to say include, but instead of including the the stdlib, stdio, and the material from the struct that I want, I'm going to include my student.h file. Student.h file. Now, one of the most important things you'll notice is that I have these quotations instead of the angular brackets that we were using before. See, in here, I'm using the angular brackets here. And when I've created my own .h file, I'm using these double quotations. See that? Is there anybody who knows why I'm doing that? Anybody who knows why am I doing that? Why is this guy doing that? Someone? All right, if there's nobody who knows that, so when we use these angular brackets, remember these materials here, stdlib.h and stdio.h, we did not create them, right? They came with a language, so to say, right? In layman's term, these two came up with a language, right? So when we downloaded, if you're using Visual Studio or you're using GCC compiler, whatever you're using, it came with these files. So when we do this include, when we are telling the compiler is that during the compilation stage, during the linking stage, remember that from computing one, the linking stage is the stage where the materials from stdlib and all these things get linked to the source code you have created. So we tell the compiler during the linkage stage, go to the usual place. So these sort of angular brackets tells us go to the usual place, which is mainly where all the other materials, library files, where they are kept. So if you were to really dig deep onto how you downloaded the package, you'll be able to find this stdlib.h where the libraries are kept. So here, the angular brackets tells the program, don't look any further, just look in the usual place, which basically where all the libraries are kept. Now, because this student.h file that we have created is not in the usual place, basically where the library files are kept, this is a file we have created and we can save it anywhere, right? So we put in the double quotation here and we can include the exact location where it is. So we can include the actual path, the file path where this file is, so that the compiler knows exactly where to look for it. Now, I have not included the path here because where this file, my allocation.c file is, and where the student.h file is, they're in the same folder. Because they're in the same folder, when we include it here, it's going just to look for it in the same folder as where the my allocation.c file is. I included there, and there's no problem. Okay, we save it. Let's try to see first for whether it works or doesn't work. Remember, I've not changed anything else. I just took up the same stuff, the material I had on the top, I just took it out and just put it in a new file, right? And then I just call it .h file, and that was okay. All right, so let's clear this. And I'm going to try running it again. But because now I have more than one file, I'm not going to try to output this. I'm going to say a war here. This command for GCC allows me to basically compile multiple files. And I'm going to say, I want my student.h file over here, and I want allocation.c file. I'm going to run this. Okay, it's complaining because, oh, this one, I think we had, I printed two things, student ID and student ID together. So maybe we should change that. We had a student ID, and this should be GPA here. Okay, so it was complaint that I'm using here, and maybe we also demarcate it to two spaces. Okay, so sometimes it's always good to get clear of the warning. All right, no problem now, everything's fine. If we do this ls, you'll see that we have a file now called a.out, which is basically our compiled file. So we can run it, a.out. Okay, enter size 5, and we can get the same data that we were getting before. See that? So I did not do anything else. I just created a .h file here. And well, I said this .h file will do the work for me. Does it make sense? And this .h file, whatever is basically having is just the declarations, right? Sorry, it's just the declarations. I declared that I'm going to have a struct student. I use a type def to rename it, and all my files, things that I will need in my code, I'm keeping that in my struct. In my .h file. And then instead of my main driver, I can call it here, main driver. Instead of my main having any other items, I just include this .h file and it works fine. Let's imagine that we had, supposing we had something that was printing for us. We had a function, supposing we had a function void, okay, print student. And what this would do, it would basically get an array of students. So it was getting something like student, like these students. It will get an array and then just print out the array, right? It will get an array and just print it. We have that code somewhere, so it's fine. So I can have that. So this is a non-value returning function, void. So we can just say return up here, you know, and that should be fine. And what we can just do is we want it to just print out this stuff. So I'll cut this and I'll just print it here. Okay, and I can change, you know, anywhere there was my student, I can just put the students. Remember, I'm not doing anything else. I'm just trying to just do the same thing that we have done before by just changing just a few materials, the names of the variables, etc., etc. Okay, so that's fine. So we basically we have a function called print students that receives these materials and just print them out. Okay, so in terms of calling that, so instead of, this was adding and printing them, so it's okay. So instead of doing anything with it, we can call the function print student. I'll call it here, print student. I'll paste it here, and then I pass my student. Remember, I do not need to pass the address of my student, although the function print student receives a pointer, my student is a pointer. In any case, even if my student was just an array, the name of an array is a pointer to the first item, so I don't need to do that, right? The important thing I possibly might need to do that is to pass how big the array is, right? So I need to pass n here. So I should add here int n, which is basically the size, int n, something like this. I need to pass, you know, how big the array is so that I can be able to loop through all the items, you know, trying to get, trying to print that. All right, save this. We tried running it again. Run it. Okay, it's comprinting. My student identifier, my student print address first element, one error generated. Okay, we are trying to print something called my student, whereas we have something called student. So here, so we change this, we paste it, no problem. We save this again, and we try running it. Okay, no problem. Compiles fine. Let's run this file, enter size 5, and it works fine. Do you see that? So the only thing I've added here from what we had before, we just created a function called print students. We'll just basically print all our students instead of us printing that in the main. And we need the array here, or the pointer. Remember, pointers and arrays are different types used in a similar manner. So I've just done exactly that, printing up, pass the array, but because we are passing an array of structs, just like an array of integers or doubles or whatever, we need to know the size of the array so that we can know until where to try to read the block of memory, which is exactly what the thing we are doing here. So we call the array and it does the assignment for us as we did before. And once we do the assignments, we do the printing out and that is done. Okay. Now, any questions yet? So far, so good? Now, this new guy that we have added here, the function, I can just remove it, cut it out, and I can just put it here. So remember, I have a file where I'm keeping all, I have a file where I'm keeping all the, so somebody say, I have a question. The values that came out for GPA was 0.00. Was that an error? Let's see. Oh, all of them are 0.00. Okay, I think there's a problem there. File in the same directory, I can see it. Okay, so yeah, I think that could be a problem. Let's try again. Let's see what's happening. No, okay. So I think that could have been just the material. It works still fine, right? I think that could have been how the, these values were, or it could have been an error. I don't know. Works fine. Yeah, works fine. I'm not sure what happened there. All right, so that should be okay. So we can put this file here, still no problem, because this is my .h file is all those other declarations that I wanted. Instead of me putting them into my into the main file or near my main function, I can just have a special place for them, and I call that .h file. Okay, so far so good, right? So what I'm just doing, this material here that I have, I can just pick it up and put them on top of main. But instead of putting them on top of main, I'm just creating a function for them, a file for them. And then I can store that file and I can reuse it in any other code that might need it, right? So I don't ever need to repeat this code. I can just put it aside. One more thing, this file, this function here, print student, it's in the same file as my allocation or my main file. And that means nobody else can use this file apart from main. So what else can I do? I can copy this guy, but because it's an implementation now containing so many things, when I create something for it, I'll just paste it here, new file. And now, because this is not a declaration, this is actually a definition. This is a definition. So definitions are contained in the .c file. So now for this file, I can call it, maybe I should call it just student.c file. See that? So now it's a .c file, and well, it will require to use it requires to use pointers, and it's printing out stuff. So it might need to have some of the materials from here. So what I just need to do is maybe, use these, because that's where my, all my materials are located, and just press it here. See that? So now, because this particular file requires to print out stuff, so it needs stdio, standard input output, and then it requires to use the struct student, and this struct student is only defined in the .h file. I should include the .h file in here so that it knows what these things are. Correct? So now I have three files. I have a header file, which is keeping all my declarations, including my function declarations. I have another file called .c file, and this .c file, student.c file, is keeping all the implementations together for me. And I have just one file I'm calling the main driver. And this work is just main, and it will call everybody else without actually much doing anything else. It's just a small file that basically can do all the stuff for me. So I'll save this, and let's see whether it works the same. So I'll clear this. And now in my wall, instead of having student.h, allocation.h, I'll have student.c as well. So I have three files now. I have student.h, student.c, and allocation.c. I run it, no problem. And then I look for the file .out. Okay, enter file 5, and works fine. See that? Don't you like that? Come on, you must like this. right? So what have we learned? We have learned that we can have multiple files. We can have a declaration file, which in this case is a header file, our own header file, keeping us all the stuff that we are declaring, right? So we are declaring all these materials, and we can have that material stored together. And we can have another file where all our implementations, for example, function definitions. So function declaration or prototypes are going to the .h files, and the function definitions or implementation of the functions, they are going on a different file on their own, and that's a .c file. And then we can have one file which has main function, and whatever that file will be doing is just call all the other stuff and bring everything to light. Do you see that? So now we are using multiple files to do our programming. This is not yet opaque, because the word opaque means something we can't see. Remember when we learned about matter in class 4 and class 5, we learned about transparent, translucent, and opaque. Remember those things? Do you remember them from class 4 or class 3? Yeah, we learned opaque objects, translucent object, transparent object, those kind of things. So we still have this word opaque that we have not come up yet about. But this where we are now, using multiple files is our way of trying to get there. So far, so good? Awesome. So I'm going to stop there. Would you like to have these files?
Yes, please.
Okay, awesome.
Yes,
I'm going to send you that files just now. All right. In the meantime, are there questions for me?
Oh, I have a question.
Go for it.
You know how on Zybooks there's like the first assignment that you have to submit to Blackboard, and then there's the vector one.
Uh-huh.
Should the vector one also have like a way to submit it to Blackboard?
Oh yeah, I should have done that. Okay, sorry, I'll do that tonight. Yeah, I'll do that tonight. The deadline is tomorrow, isn't it?
I think it's due today at like 11 p.m.
Yeah, and I think the first one is due today, and the first. Oh yeah, today is the second, right? Today is not the
Mhm.
first. Second.
Right.
Okay, I'll do that. I'll put it up. I will make a link that basically is able to do that immediately
All right.
after this class.
Thank you.
No problem. Okay. I'm sure it has been an exciting class running about all those new things. Those are new things, right? It's exciting learning about those new things. So we're going to conclude there. Thank you for coming. I'll see you again on Thursday. Have a good one.
Wait, how do we send the vector once we complete it to this house?
Oh, I'm going to make a link onto Blackboard, and then you go onto that link, you click on it, and basically it will ask you to do the work from Zybooks, and then it will transfer the grade.
Okay.
If you already did it and you don't want to do it again, that's still fine. I'm just going to ask the TA or the grader to upgrade those files.
Okay, so a link will come up momentarily that will let us link it to Blackboard.
Yeah,
Okay.
yeah, I can do
Okay.
I can do that like in 2 minutes.
Okay.
Awesome. Have a good one, everybody.
All right, you too.
Thank you.
Thank you,
too.
Professor.
Yes, thank you, everybody.